Good evening, sir.
Hi, good evening. So we'll wait for 1 or 2 minutes and we'll start by 6:03 or something. All right, so we'll start the class. So today the main objective is to see how to use the packages that we have learned till now, like different packages we have discussed, like pandas, NumPy, then visualization tools. So we'll make use of everything and we'll try to solve this predicting price of cars problem. That is an end-to-end regression problem. So we'll see how to do that. So here is a brief overview of what we are going to do today. So we'll start by loading the data set and we'll see how the data set looks. Then if there are outliers or missing values, we'll deal with that. So that comes the feature engineering part. Then we'll try to visualize the relationship between features and the target variable. And we will try to build two types of models, that is linear regression and random forest. And then one on two versions of the data, like if we have any missing values, I think in this data set we have. So in one case, we'll be using or we'll be avoiding the missing values, all the samples, or we'll impute the missing values with some data and we'll try to solve the same problem. All right, so the data set that we are using is cars sampled.csv. I hope the same data set is available in the Swayam website. You can download it. So here we have the data set. So it's kind of difficult to understand. So yeah, so it's a CSV data set. We have the date, name, seller, offer, type, and etc. Different features we have. So we'll see how we can use the Python tools to load the data, then and for further processing. So let's start. First, we'll see what all libraries are required for this. So pandas, we know for data manipulation and analysis, we use pandas. The NumPy for different numerical operations. And here we use a Cbond package for statistical visualization. All right. And also matplotlib is also being used for different plots. So first we are importing the libraries. So these are the standard formats that we have: pandas, NumPy, Cbond, and matplotlib. All right. So let's load the data type. So we are using the pandas library to load the data type using the syntax pd.read_csv, and then we have we'll give the file name. So we read the CSV file into pandas data frame. Then we know that we are making a copy of it. It's a good practice to preserve the original data. So like if you are making any changes to the data, the original data is always preserved under cars_data. So we are creating a working copy to preserve the original, that is using this dot copy syntax. So here we have, so if you look at the shape, so it has 50,001 rows and 19 columns, means it has around 50,000 samples. One row should be the header row, and it has 19 columns. That means 19 features. So let's explore the data. So first, we'll be using the .info command, which gives a summary of the data. So it will give the column names and data types, then count of non-null values. So it's very useful if you want to spot any missing values. And also it gives the memory usage. So let's try to do that. So we have the data summary or data info. So if you see, like most of the rows, we have the entire data, whereas vehicle type, we have only 44,000 data. So there are not NaN values in some rows under their vehicle type column. Similarly, under gearbox, we have NaN values, and model we have NaN values. Then fuel type also we have less values. And if you see not repair damage, it is having only 40,285 full rows. So if we go by the way, like omitting the NaN values, we'll have in total the final model will be using only 40,285 rows. So now let's look at the statistical description of the data. So we have the minimum, it will give minimum value, then first quartile value, median value, then third quartile value, and maximum value. And also it gives the mean and standard deviation of all numerical columns. So let's see. So the price, we have 50,001 count. Then the mean value is given, standard deviation is given, minimum value is 0, and maximum value is also given. Similarly, for other year of registration, hour, kilometer, month of registration, postal code. So all these are numerical columns. So using the describe command, we can get the info of the numerical dataset. So let's see. Let's try to clean the data properly. Like we will first drop irrelevant columns. So our main agenda is to predict the price, right? So what are the columns that we can omit, or some of the columns that we don't need to predict the final price. So some columns carry no predictive value, and it can only add some noise. So like the car name or the title. So it's actually it might matter, but as far as our model is concerned, it might be interested only in numerical data types. So we are omitting the name column. So the car name or title, which is either too unique or it's not much generalizable. Then date crawled, that is a metadata about the when the listing was scrapped. Then date created, that is when the listing was created. Then postal code. So there is no meaning like what postal code and the price. Does it really matter? We don't know that. But in this case, we are omitting that column also. And last seen. So last seen is like when the listing was last visible. So we are omitting these columns. So we create a list of columns need to be omitted or need to be removed from our data. So we have 1, 2, 3, 4, 5 columns. Then we simply use dot drop columns names and axis. So after that, if you see the remaining columns, we only have 14 columns. Initially, we had 19 columns in total, 19 features. Now we are left with 14 columns after removing these 5 columns. Now we will look for duplicate records. So there can be whenever we are making manual entry, there can be chances that the same data is entered twice or thrice. So we have to avoid that because that can affect the model performance. So duplicate rows can skew the model training by over-representing certain patterns. So we keep first occurrence and drop any subsequent duplicates. So let's see what is the length of the cars before. Then we'll dropping the duplicates using the command drop duplicates. And we are also outputting how many data is remaining. Then duplicates removed is before minus after, and we'll be finally see how many data or samples are left. So we can see that we have 470 duplicates, so which we have removed, and finally the total number of samples we have or total number of data or rows remaining is 49,531. Now initially when we checked the info, we know that there were missing values. So this is just seeing in each of the column after removing the duplicates, how many are still missing. So the highest number goes under not repaired damage column, that is having 9,640 missing values. All right, so let's see the outlier and the working range, because in some columns can have too much of outliers, so that can make our model training not efficient. So several numerical columns have extreme values. So like example, in our data, when we first checked, the info, we can see that the price is 0 or very less values. So that may be, or the power of a car is 0, month of registration, that's fine. That's also 0. That may be also error entry. So those extreme values we have to avoid when we are training our model. So let's see. So some examples are a car registered in 1000 AD or price of very less value. So we'll investigate each and define a sensible working range. The first is the year of registration. So what we are going to do is cars registered before 1950 or after 2018 um, are unlikely to represent real used car listings. So visualize and count these outliers. So let's say, so we are creating or we are slicing our data to get the year of registration column. And so the distribution of registration years is saved in year-wise underscore count. Then we have, let's see how many are above registered year of registration is greater than 2080 or less than 1950. So we're using the conditional statement here. Then we are using the regression plot where X is the year of registration and Y axis shows the price. All right, so let's see. So this is the working range. So this is the year of registration versus price before filtering. So you can see that some of the price here are too much. So let's see. Now let's see the next that feature, that is the price. So the price below 100 euros or something are likely data entry errors or free giveaways, we can say. And price above 150,000 are rare or luxury or exotic cars. So that would those are very rare cars to be listed. So that can distort the model, our data science model for typical used car market. So let's plot that one also. So we have, so this is a description of the price column. So still we have the minimum 0 value, then maximum some random number they have entered. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the price distribution as we can see. So we have a lot of price scattered around this 0.0, very near to that. Remember, this is under at a scale of 1 to 1 into 10 raised to 7 scale. Similarly, if you see the box plot, so box plot, you know that it gives the outliers. So here we have a lot of outliers. And if you see the data, the price above 150,000 is 34 and below 100 is 1748. Now let's move to the next feature. That is, I will avoid the power values below 10 and above 500. So let's plot it. So here also we can see that the power distribution is more or less concentrated here, and we can see there is outliers. So above 500 PS we have only 115 vehicles. So that is affecting our overall distribution. So if you look at the plot of power versus price, so finally we have to predict the price. So always it's ideal to plot a plot between our feature and the target. So here we have the power versus price scatter plot. Here also we can see that we have outliers here and here. Now let us filter our data. So we filter our data set to keep only the records within the sensible ranges that is identified that we have identified above. So let's see our cars registration we are taking into account between 1950 and 2018. Then car price we are considering between 100 and 150,000. Then power we are considering between 10 and 500, including these values. So let's see how much data that we have removed because of this. So before filtering, we had around 48 or 49,531. Now we have reduced our data set into 42,772, and we have removed around, or we have filtered out 6,759 data. Now we are adding one more feature. So sometimes we will have a lot of data in different columns. So some data, if we add, it becomes more meaningful. So what we are trying to do is, like, instead of using year of registration and month of registration as two separate features, so we combine them into a single, more meaningful feature, that is the age of the car. That is in years as of 2018. So age is equal to 2018 minus year of registration plus month of registration divided by 12. So what it does is it gives us a continuous variable that captures both year and month precision, and then we can drop these two columns, that is year of registration as well as the month of registration. Both these columns can be dropped from our data set. So first we add first we normalize the month of registration column, and then we just create a new column, that is age. And finally, we are rounding off the age column to a decimal place of 2. All right. So let's see what our age column looks like. So we have 42,772 count, and the mean and standard deviation are here. Then minimum age is 0. Maybe it's a vehicle registered in 1950, and maximum is 67.75. Okay, then we are dropping these two columns. So here we have dropped 2 columns. All right. So now we have done our part of adding new column and then removing the unwanted columns. Now let us try to see how different different feature distributions and their relationship with our target price. So let's try to plot it. So now we have the age distribution. Still we have some outliers, but at least the data is pretty much distributed. Then we have the box plot for the age. Then the price distribution we have here with the count. Then price box plot we have. So if you earlier when we saw the plot, well, let me go back. So this was our price box plot. So we were seeing a lot of outlier or very much skewed data distribution. So now after removing the core, after filtering the data, we can see that the price box plot, we can see the minimum, maximum, and the distribution. It's may not be that great, but still it is good considering the previous version. Then we have power plot. So power also distribution, we can see that it has been distributed very nicely. And this is the box plot. Now let us see the relation between numerical features versus the price. So here we use the scatter plots. So our target variable is price. So here we have the distribution of age versus price. So maybe higher age vehicles, and so these must be the exotic vehicles that we were talking about. It is having higher age, but still it is priced at very high value. And there are also vehicles which are very less priced, or we cannot see a specific pattern from this. Whereas if you see here, it's kind of obvious that as power increases, the price is also increasing. So it's kind of like growing with the power. The price is increasing with the power. So what we can observe is as price increases, as age increases, price generally decreases. But some high value cars exist across ages. So that can be the classics and collectibles. And if you look at the power versus price, it is obvious that the higher engine power correlates with higher price. Now let us see the categorical feature analysis. So for categorical variables, we cannot directly take any scatter plot or something like that. So we will use the frequency distribution and their impact on the price. We'll see that. So we have only one type of seller, that is private, no commercial. All right. Then we have offer type. It's also only one type. So nearly all the cars have offer. So we don't see any variability, or it's or that column is insignificant. Then we have absent value count. So no, not absent, A/B test value count. So here we see that the vehicle which is under having A/B test and control, so it is having almost equal split, almost 50-50 split. So there is no difference in price. So it also makes it insignificant. Now let us move to the vehicle type. So we have, so let's see what are the vehicle types you have. So vehicle types, you have the limousine, small cars, station wagon, and we have around 1, 2, 3, 4, 5, 6, 7, 8, 7 types of specific types, and and then other category. So we have total 8. 1, 2, 3, 4, 5, 7. So total we have 8. So if you look at this, yeah, there is a difference. Like, so the count of limousine is highest, followed by small cars, then station wagon. So there is vehicle type clearly affects the price. So if you look at the price tag of vehicle types, it's not equal. Like each type is having different price ranges, or even the mean value is different for each of the vehicle types. Now, automatic versus manual. So if you look at the automatic versus manual calculation, it is also having significant difference in the mean value. So we'll include the vehicle type and the gearbox type in our model. Then the odometer reading, that is how much kilometer the vehicle has run. All right, so it means like there are cars which have run more than 140,000 kilometers highest. So if you look at the price range, the there is variability seeing. So it can be because different cars might have run different kilometer range. Next comes the fuel type. So here we have like kind of 7 categories, and the most is petrol fuel type followed by diesel. Then we have very less electric cars or the hybrid types. And here also we can see the difference in the price. So we can say that the fuel type also affects the price of the final price of the used car. Now the brand of the car. So yeah. So I don't know how many brands we are listing here. All right, so we have kind of so maybe more than 20 or 30 brands we have. So we can see that the most of the cars are from Volkswagen, followed by BMW, Opel. So the price also is dependent on the brand. So if you look at here, the Porsche is having higher mean value because it's a sports car. So most of the cars will be on that level. So I think this is from, and their data is from European market. So there are a lot of brands which are not familiar for us. Okay, so we can say that the brand of the car also affects the price. Now another data is not repair damage. Yes means the car has damage that hasn't been repaired, but no means the car has damage but it has been repaired. So we can see that the yes is having less count, but the car which is having damage and is not repaired is also sold for very less value because we know nobody wants to buy a damaged car. Now we'll remove the insignificant variable. So based on our data analysis, three variables showed no meaningful relationship. That is seller, offer type, and A/B test. So we will drop those three columns. So here we have, after dropping, now we have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns we have. Now we compute a correlation matrix for all numerical variables to quantify linear relationship with price. So a high absolute correlation value that is close to 1 indicate so strong or higher correlation. So let's try to do that. So here it is. So if you look at, so it's so yeah. So it's better visualized this way. So price will go with price in one will have the highest correlation with each of the variable will have highest correlation with itself, and our aim is to find the highest correlated against the price. So if you look at the power and price is having 0.58. So we know that that is having kind of a strong positive correlation. So whenever the price power increases, price also increases. Then kilometer and age is having negative correlation. That means when kilometer is higher, the odometer reading is higher, the price goes down. Similarly, when the age of the car increases, the price again goes down. So you can see the different how different features are correlated to each other. So here, if you see age and kilometer, we can see that it is having a positive correlation, which means that as age increases, the kilometer is also higher. Now let us prepare our data for final modeling. So we'll train on two versions of the data to compare the effect of missing value treatment. So one is by omitting the data, that is any row with any missing value are dropped. And in the second case, we'll be imbue to the data, that is missing values are filled with the median in case of numeric variables or mod in case of categorical variable. So first approach is by dropping the missing values. So we just use the command drop nan values, that is drop na, and drop all rows with missing variables. So finally, we have dropped around 9,888. So finally, what we have left is 32,884 samples. All right. Now we are using the modeling libraries from scikit-learn package. So we have the first we will use the train test split. Then we have the linear regression model, which will be used, and also we will use the random forest regression. And to calculate the loss, we will be using mean squared error. So first we will import the libraries. Then we are building the model. So to build a model, so what are the required things? So first we have to identify the features and target. So, and usually we do the log transformation also. So why we should do the log transformation? Because we have seen that our price distribution is a little right skewed. That is very few expensive cars are there. So applying a log transformation will make the distribution more normal or symmetric, and it makes the linear regression assumptions more valid, because in linear regression it assumes that all the features and target are normally distributed. Then we'll be using our 70% of data for training and 30% of test. All right, so let's first X is the features. So from our data set, we will drop the price and we create the features. Then Y1 is the target. So we will just use the price column from the data. All right. So let's. So this is the log transformation, how it transforms our data. So this was the distribution before transforming, and this is the data. This is the distribution after log transformation. All right. So we are applying the transformation here and performing the train test split. So here we are giving test size is equal to 0.3, which means 70% of the data goes to training and 30% goes to testing. So random state we are defining as 3. So we can use any number here so that we can reproduce the results. So if you change this three, a different train test split will be created. So here we have the data. So finally, we have 23,018 data for test training and 9,866 for testing. So first we are um, a baseline model that we are creating, that is using the omitted data. All right, so our target is to reduce the root mean square error. So mean of the log price on test data, that is 8.2496, and baseline RMC is 1.1274. Now let us do the regression. So this is our model that we are initiating from the linear regression class. So we are initializing and fitting the linear regression model. So to fit the model, we just need to use the model dot fit. Then we have to give the features and target values. Then we will predict the uh, values of the test data, and we use the mean squared error, that is y test is the true value and predicted value is cars predicted used after training the model. So this is the mean squared error, and by taking the square root we get the root mean squared error, and we will also calculate the regression score, R square score, for both the test and train data sets. So the RMC is found to be 0.5456, and R square for test is 0.76, and for train is 0.78. So it's obvious that the R square will be better for the train data, because the model is trained using the train data, and test data is something that the model has not seen. Now let us plot the residual plot. So residual is y test minus the predicted value. So for an ideal case, the residuals should follow the zero line, but our model has predicted quite good, but still there are some higher deviations, like minus almost equal to -6 or 4, but almost all the data is scattered around the zero line. So now let us use the, so now we have used the linear regression model. Now let us use the random forest regressor by omitting the uh, using the same data. So what are the advantages of random forest regressor? So it's an ensemble model, like there can be different branches or different decision trees, and then each decision tree is trained on a random subset of the data, and finally what we are predicting is the average of all the trees. So some of the advantages are it captures non-linear relationships, then it is robust outliers, then it handles features interactions automatically, and also it is having higher accuracy. Okay, so here are the some of the parameters that we use when we initialize the random forest model. So here we are using 100 trees in the forest. It's like we are using 100 different decision trees to predict. Then the depth. So it's like how we can say one node will be having two different nodes and so on, like a pyramid scheme. So that is the maximum depth representing. Then we have the splits and the leaf. So to give an intuition of what random forest is, we just see. I'm not able to. Okay, yeah. So here is what a random forest look like. So data set is split into different trees. So this is first decision tree, second decision tree, third decision tree. And we have the depth denotes how much depth the tree can go. Like here it is 1, 2, 3. Then estimated is the number of trees. Then split means um, it's kind of like how much samples are required in these different splits from one node, and that the leaf is the end, how much should be there. So here is the random forest regressor. So first we initialize the model using the parameters, then we again use the fit command model.fit, and the same whatever we have used for the linear regression is used. So we can see that the final result, the RMSE is reduced and we have an improved R square for both the test as well as train compared to the linear regression. Now we are moving to the second approach, that is by imputing the values. Imputing means we are filling the NaN values with something meaningful. So for numerical columns, we'll be using the median, and for categorical columns, we'll be using the mode of the distribution. So this is the command to impute the values. So we are applying fill the NaN values with the median, or if so yeah, else we are counting with the mod. So this is for so in case of float data type, we'll be using the median or we'll be using the mod. All right. So if you look at the data after imputation, we can see that the NaN values, or there are no rows having missing values. So we have imputed all the rows with some values. So again, we are using the same technique, like we are dropping the price from the features, then Y2 is our target, and we are splitting the same 30-70 split, and we are using the same random state. So this is the visualization again after applying the log transformation. So yeah, the linear regression, the same steps are followed. First, we initialize the model, then fit using the train data and target data. Then we predict the test data, we predict using the test features and compare the or compute the MSC using the test true data, that is y test, and the predicted values, and we calculate the different mm, values. So if you see the linear regression values, when we imputed, actually the RMSE has increased and both the R square values has decreased. Now let us see how it performs when using random forest regressor. We can see the same results when using random forest regressor also. So even though there is improvement compared to linear regression, but the performance is not as good as when the omit when the NaN values were omitted. Now let us print the whole summary. So this is for missing values omitted model. So the baseline was 1.1274, and when the values were imputed, we have the results here. So lower the RMSE, the better the model, and higher the R square value, the model is better. So let's try to compare visually. So we can see that the baseline imputed is higher. So is the RMSE of imputed linear regression as well as the random forest is higher. And for R square value, the higher is the best. So the omitted model gave the better performance in case of linear regression as well as using random forest. So the key takeaways that we have in this notebook is, so first we loaded the data, then cleaned the data, then we handled the outliers, that is by filtering. Then we added a new feature, that is age, using the year and month of registration columns. Then we identify different features which were not significant or which were having high significance. Then we trained and compared 4 models using 2 data treatments. So this is our final model insights. So we have the lower the RMSE, it's better. So the baselines omitted, it was 0.66. So it's better than baseline, but the random forest omitted is the best. Again, the imputed, also the random forest imputed is the best. It is substantiated by the R square test value also for the random forest model. It gave the highest R square test value. So in this model for this data set, we can say that the random forest outperforms linear regression. So what we need to understand is that the relationships between different features and the price are not non-linear, and the ensemble model by the random forest handles feature interactions better, or more non-linearity is given by the random forest model. Then imputation versus omission. Even though imputed data retains more records and better performance because we are having more number of data, but in many cases, like as shown in this example, dropping rows loses potentiality, but sometimes it is better to drop the rows other than um, giving false data and doing the model training. Then a log transformation that we have to do, because we haven't done our model training without log transformation, but it's always recommended to do the log transformation. Then also the feature selection also matters, that is dropping insignificant rows and including the or giving higher priority to the significant rows. All right, so here is the final takeaway for the regression case study. And next we will see the uh, logistic regression. So before that, we'll take a 5 minutes break and we will start at around 7 o'clock. So if you have any questions regarding the first regression case study, you can ask now.
Sir,
Yes.
sir, can you
Yes.
hear me?
Yeah. Yeah.
Sir, actually, for regression, like you've taken test data and train data, no, sir.
Mm-hmm. Yes.
So for that, how can we select which is test and which is trained, sir?
That is entirely random. So here we are splitting the data, right? So it's entirely random split. So we don't know whatever rows will go to train, whatever rows will go to test. But whatever data we have, it's entire data that we have. And what we can do is, so if we change this number and we again do the train test split, we'll get in the when we done the same thing previously, some data from the test will move to train set and some data from the test train will move to test set. So it's not important which goes to which, but the thing is, um, if we do the train split manually, so let's say what we, so here we have the total data. So if you are taking first 100 into test to train and not 100, so how much it should be? 23018. Okay, some percentage. So let's say 0.7 into length of x1. So this is test and this is so that is train and this is test. So if we do this, there is a chance that the data is not shuffled properly, and some of the so let's say we had different category of data. So maybe a particular category can go to the training set, so that the model will learn only uh, on that model, on that particular class of items. So we can do this test restraint split manually, but it's always recommended to use the uh, train test split function from the scikit-learn, so that the data is randomly distributed and all the classes are considered when the final train and test is created.
Sir, what if we
Okay, sir.
don't have this numerical and the integer data? We have the image. So how we can how do we define the feature, and how do we engineer this feature? Like we want to classify the images based on the real and fake. So how we can build the feature engineering and exploratory data analysis?
So in such cases, how the data will be prepared is, um, so let's say, we have the CSV file. So each sample will have image, just image we'll have. So we'll have just image. Then the target will be it's fake or real. So just one column will be only images. Then we have so let's say, so if you see, so we'll have image, then fake. So let's say image one, fake, then image two, image three, image four, image five, image six. Then we'll have real, real. Say so this is how the data will look. So it's not a tabular data as we have seen here, like in a CSV file. So it will be like we'll have the images, and correspondingly it will be either fake or real. And in such cases, we won't be using linear regression models. We'll be using classifiers. So we'll have the, especially in case of images, we'll be using convolutional neural networks, so which can learn the features from the image. It's not like we will have the that one pixel value in each of the columns. So finally, everything is numbers. So image is nothing but a matrix of numbers having different values from 0 to 255. And the computer will, or the model will use networks like convolutional neural networks and train the model. So the final target will be, so the in such cases, in in the model that we have discussed, the inputs were different. So where were the columns? So yeah, so input were these 10 columns. So in case of the image classification, the input will be the image, and the target will be either fake or real. So it's not a tabular data as we have seen now.
Sir, is there any other ways rather than CNN?
Other than CNN, other than CNN, what do you need to do?
Sir, better for the better accuracy.
So for better accuracy, you can use vision transformers. Even that uses CNN, I think. So at first we need to read the data, right?
Yes.
So in order to read the image, CNNs are better. So once the CNNs read the data, or the convolution layer reads the data, it will create vectors based on the image. And finally, that vector is processed in the final stages to get the final output.
Yes.
Yeah.
Thank you, sir.
Yeah. So I'll just take a 5 minutes break, then I'll be back by 7:10. All right, we'll continue. So now we'll see a classification problem. So the first one was like predicting the car price. So now we are trying to do a binary classification to predict whether a person's annual income is less than 50,000 or greater than 50,000 based on the demographics and the employment data. So again, we have the EDA part. So understanding the distribution, relationships, and missing values. Then data preprocessing, visualization. Then we'll use the logistic regression using all the features, and we'll use also logistic regression using a reduced model, that is by removing the insignificant features or variables. All right. So again, the data you can find it in the SYM website or NPTEL website. So yeah, let's see. So let's just look at the data once. So here is the data, different columns. And finally, the target is the salary status. So it's less than or equal to 50,000 or greater than 50,000. So only two classes are there, the salary status. So we'll convert this less than or equal to 50,000 into, so that will be converted into 0, and greater than 50,000 will be 1. So again, we have the different tools needed. So pandas, NumPy, Seaborn, then train test split. Then we are using a logistic regression, that is the classification model. Even though logistic regression is called regression, it is a classification model. So that has to be so logistic regression is a classification model. Then we'll evaluate our performance using accuracy score and the confusion matrix. So here we are importing the required libraries. Then data is being loaded. So the data is income.csv. And we are creating a working copy of the data. So here we have 31,978 rows and 13 features or 13 columns. So this is the initial data that we have. Raw data without any manipulations. So let's again take the info of the data. So we have, so this data is pretty good, right? So there are no null values. So whatever 31,978, all the columns are filled. So yeah, so we're checking for any missing values, that is 0. It's pretty good. But we'll have to see if the, so when we are using these info or using this is null equal to sum, only the columns which are nan will be captured. So let's see the statistics of the numerical data. Okay, so these are the data that we have. Now we'll check the categorical data description. So let's see the missing values, if there is any. So we found that dot nine values are not there. So but in some data sets, the missing values are sometimes encoded using strings other than NaN. So let's see the unique values in job type and occupation. So we can see some entries like space and question mark. So these are the real missing values, but it will not reflect in when we use is not function. So if you see the unique values in each of these categories like job type and occupation, we can see that question mark values. So those values should be avoided while training the model. So though both these categories contains these entry, so we must reread the data treating these as NaN. So let's do that. So here we are defining the NaN values are denoted by a space followed by a question mark. And if you see now, we can see that the NaN values are there in job type and occupation. So some of the observations are job type and occupation have missing values. Okay, so let's see.
Excuse me, sir.
Yes.
Sir, actually, I am Kavin. I have actually we had in our college we had past 2 weeks we had assessment exams, sir. So I was unable to finish these assignments in the given in the NPTEL, sir.
Okay.
And they have past 3 assignments I haven't completed, and it has been locked, sir.
Yeah, the date, I think the date has been finished, right? The deadline is over for those first 3 assignments.
Yes, sir. So
Yes.
what should I do if I gave any request? Will they open it or?
I don't think they will open, but better you do the fourth assignment, and I don't know how it will affect the final grade. Maybe you can mail once the NPTEL team and ask. That will be better because
I
it's
should
not
ask.
in my control.
Okay, I should ask the NPTEL team, sir.
Yeah, you have to ask the NPTEL team.
Okay, sir. Thank you, sir.
Yeah. All right. So where were we? Okay. So it's important to see the values in the different. So it is important to do the EDA or analysis of the data. Otherwise, our final model performance can drop. All right. So let's. So here we are dropping the rows with missing values since the. So here the problem is the missing values are concentrated in two categorical columns, and we have a large enough data. So we will drop the NaN, the rows wherever the NaN is there. So we have dropped only 1,816 rows. So finally we have 30,000 samples or data. So let's see the correlation map, heat map. So we'll just linear correlation between the numerical features, and we'll see which are highly correlated. So maybe we can say that cannot see which one is highly correlated. Maybe age and hours per week is having the highest correlation.
Excuse
So
me,
let-
sir.
Yes.
Sir, I am a BSc mathematics student and I have some prior experience with RStudio, and now I'm going to complete the course for Python. So I wanted to ask if this is enough for internships, or should I try to gain some more skills before I can apply for them?
Internship in what kind of roles? Data scientist roles? Or,
Yes, sir. Could you also guide me on what kind of roles would be suitable?
for the thing is, it all depends on the companies you are applying to. So it's good to show some projects in data science in portfolios. But I don't know how. So you are still doing your BS.
Yes, sir.
Okay. So yeah, you can show this course and some projects, independent projects that you have done using what you have learned in the course. That can add some value.
Okay, sir. Thank you, sir.
So let's try to visualize our clean data and focus on how each feature relates to the target variable, that is the salary status. So this is our available columns, and let's see how the gender affects the salary status. So if you see greater than the 50,000, the male is having a higher count. And if you see the salary status is less than or equal to 50,000, in that case, females are uh, in higher number. So now let us see our data, whether it is kind of balanced or imbalanced. So if you plot the salary status column, so you can see that the most number of rows have uh, less than or equal to 50,000. So that is having around 22,000 numbers, and only 7,500 is greater than 50,000. So it's kind of skewed, like 75 percentage of our data belongs to uh, salary less than 50,000, and remaining 25 percentage is for uh, greater than 50,000. So there is a moderate imbalance in our data set. So our accuracy benchmark must account for whatever the data skewness there is in the data. Now the age distribution and age versus salary status. So if you look at the count, the mostly the age around mid 40s, 30 to 40 range is having highest number of count, and the highest salary is for greater. The main age for higher salary greater than 50,000 is like more than 40, whereas it's kind of less than 35 when we see the salary category less than 50,000. So people aged 20 to 45 are most frequent in the data set. So here is that frequency. Then we can say that 35 to 50 are likely to earn 50,000 and above, and 25 to 35 are more likely to earn 50,000 and below. Now we have different job status. So in private sector, we are having salary, a more number of people earning both the salary category And yeah, in except in self-employment, I think this is self-employment. In all other categories, the persons earning less than 50,000, number of persons earning less than 50,000 is higher. Now the education type versus the salary. So high school grad, some college, 9th, bachelor's, and so the highest number for greater than 50,000 have at least a bachelor's degree. When we have master's degree, it seems the number of people earning greater than 50,000 surpasses the number of people earning less than 50,000. And professor, all those or doctorate status also has the same trend. Now, in types of occupation, for the critical jobs, the number less than 50,000 surpasses by great amount. Similarly, so we can see that a comparable status is shown in categories like professional specialty or executive managerial post. Other than that, there is a difference between a high difference between both the salary status. So these are some other capital gain and capital loss distribution. So these are financial variables. So both are expected to be highly rightly skewed because most people report zero capital gain or losses and with a few extreme high values. So this is most of them are reporting zero capital gain and very less people are actually admitting to having a higher capital gain or higher capital loss. So let's see what is a logistic regression. So logistic regression is is a supervised classification algorithm that models probability. So the final output will be something between 0 and 1. So it's actually outputting a probability that an observation or the features that we give belongs to a given class. So it's like, unlike linear regression, its output values are always between 0 and 1. That is, at the output layer, we will use the sigmoid function, so which is given by here. So this is the function giving the sigmoid function. It's 1 divided by 1 plus e raised to minus. So these are the different weights, and x1 to xn are the different features. So typically we will keep the threshold as 0.5. So whatever above 0.5, so we see that the output values will be between 0 and 1. So whatever the values between above 0.5 will be classified as class 1, and less than 0.5 will be classified as class 0. So first, so before doing anything in our classification problem, we have to set our, or we have to encode our salary status column into 0 and 1. That is, we map them to binary integers so that the scikit-learn package can process them. So we are changing the salary status wherever the 0 less than or equal to 50,000 comes, it will be changed to 0, and wherever greater than 50,000 comes, it will be changed to 1. So that so after doing that, we can see that the salary status has been moved to 0 and 1. 0 having 22,000 something count, and 7,500 for the category 1. Now we will do the one-hot encoding. So what is one-hot encoding means? So different categorical data we need to convert into numbers. And in one-hot encoding, we convert all the categorical columns into binary indicator columns. So how is it done? So let's say in our let's take if we have a column like season. So season we will have winter, spring, autumn, or let's say summer and rainy season. Again, let's say early season, spring. So these are different seasons that we have. So now, once we do the one-hot encoding, we will have so what one-hot encoding does is we'll add more columns like winter, then spring. So now we are doing the one-hot encoding of the seasons column, and we have the rainy and summer. So depending on this column, the winter will be 1. And we have spring 0. Rainy will be 0. Summer also will be 0. Right. So now for the second corresponding to the spring, we have 0 everywhere else and 1 below the spring. Similarly, for summer, we have 1 in the summer. Then for rainy, we will have here we will have the 1 and spring. So this is what one-hot encoding does. Then drop first equal to true means after doing the one-hot encoding, we'll drop the seasons column altogether. So what remaining will be the winter, spring, rainy, and summer. So this is how to encode, or under one-hot encoding, we'll encode the categorical data into 1 and 0s. All right.
Sir, if we have more than one categorical column, it works the same way.
Yeah, it's works the same way. So this is the heading of the categorical column, and we have different categories. So similarly, if we have different column, we add more number of columns.
And how will it identify which column we are trying to, for which column we are trying to apply one-hot encoding?
That we have to give.
Where do we give that, sir? That column name? Here, like you are showing it for, yeah.
So here we are doing it for all the columns.
Okay.
So let's see. So here we had the job type column in earlier case. So after one-hot encoding, we have a job type underscore local government, job type underscore private. So those all are the new columns that has been added. All right.
Right. Yeah.
So
and the original one gets deleted.
Yeah, original one gets deleted. Okay. So here is the another column, ED type. So let's see. So occupation we have done. So all the categorical columns will get automatically done. And if you want to do for specific column, you can give that also under here in this data.
So we write
here-
the name of the data frame and within square brackets we put the column.
Yeah, bracket you can put the columns.
Okay. Thank
All
you.
right. Yeah. And now we do the same what we have done for the regression problem. We will separate the target and features. So Y is the target and X are the features that we have. All right. So here we are just creating a list of the feature columns, of the name of the feature columns. So finally here we have total 94 features, and the target is either 0 or 1, that is. And again, we are using the same train test split, and 30% for testing and 70% for training. So here we are initiating the model. Then maximum iteration we are setting to be 1000 for convergence. We can how if we increase the iteration number, we'll have a better model. But sometimes it can overfit the data and can cause generalization issues. So the prediction will be bad in such cases. So here we will fit, and so this is what is giving or the intercepts of the model. So these are the coefficients for different variables, and this is the intercept of the model. So what does these coefficients means is that a positive coefficient means increasing that features raises the probability of winning greater than 50,000. A negative coefficient means the opposite, that is the magnitude, and the magnitude indicates the strength of the effect. Now let us try to predict our or try to test the performance of our model by predicting on the unseen data. So we have the sample prediction for 20. So this is the predicted, and this is the actual values. So we can see that zeros mostly has been correctly predicted, but one has been predicted as 0. Similarly, 0 has been predicted as 1. So we have differences from our model. So here we have correct predictions. All right, so let's see what a confusion matrix does. So confusion matrix is something useful in classification. So it gives mainly 4 values: true negative, true positive, false negative, and true positive. So the confusion matrix breaks the prediction into these 4 quadrants. So if the actual result is 0 and predicted is 0, then it is a true negative. And then if actual result is 0 and we have predicted it 1, which means we have predicted something is negative as positive. So it's a false positive alarm. And if we have predicted an actual positive to be negative, then it's a false negative. And an actual positive being predicted as positive is a true positive. So in our cases, true negative means correctly predicted less than 50,000. True positive means correctly predicted greater than 50,000. The false positive will be something which is predicted greater than 50,000, but actually it is less than 50,000. And false negative will be something which is greater than 50,000 is predicted as less than 50,000. So here we have the confusion matrix for this model. So here This is greater than 50,000. So it's correctly predicted 1,302 times, whereas 6,318 times it has been correctly predicted as less than 50,000, whereas we have 924 plus 505 false alerts. Now, accuracy matrix is calculated by calculating true positive plus true negative divided by the whole. True positive plus true negative plus false positive plus false negative. So in our case, the accuracy score is 0.84. That means we have around 1,429 out of 9,049 as misclassified. Now let us try to remove some columns and again train the model. So we are removing gender, native country, race, and job type. All right, and let's try to train our model. So these are the same steps that we have followed, but we can see a significant reduction in the number of features. I think earlier it was around 94 features we were using. And now we, after removing these 4 columns, we have only 43 columns remaining as features. So again, we do the same split and we have the result here. I don't know if it has improved. So let's see the accuracy score. So accuracy is 0.83. Earlier it was 0.84. So having higher number of features is better in this case. So this is the final comparison. So the full model had 84% accuracy and reduced model have only 83%, almost equal. So here is the final comparison. So misclassification has slightly increased in case of reduced model. So in this logistic regression, we loaded the data, then inspected, and instead of NaN values in our data, we had these question marks. So we had to handle that. So we had to reload the data with proper NaN values. Then we explode all the key features against the target. Then 2 regression models were created with all features and one with less features. And we found that in our data, we had a little class imbalance, that is around 75% of the people that we have sampled were of one particular class. Then we also saw higher degrees correlate with the higher salary. And we also see some of the categories were highly skewed. Then the model performance, even though it reduced when we removed some of the columns, but it was not that significant. So the reduced model can be preferred if we are considering a simpler model or a faster model, and it's easy to understand. So yeah, so logistic regression can be used for binary classification. Right. And you can also try these things. So we have different models like random forest. We have already seen. You can use random forest for classification also. That can also be tried. And we have XGBoost model also, which is also pretty good. Then we have different scores like precision, recall, F1 score, etc. All those can be reported as an additional metrics. All right, so that's it for today. So if you have any doubts, you can ask, or else we'll close the section. All right. So if you don't
Hello.
have, yeah, please.
Can we get this IP via NV file?
Yeah, I will upload this in the drive.
Okay, sir. Okay, thank you.
Were you able to access the previous files, or do you have
Yeah,
the link?
recordings are available, but files are not visible.
Files are also in the same document, right? That was shared. The
Okay,
Excel
okay,
file.
sir. Okay,
Yeah,
I
you
will
can
look into
find.
it. Sir.
Yeah, I will upload that. All right. So thank you for joining.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
Yes. Thank you all.
Thank you, sir.
Thank you, sir.